let's finish up this review. It's kind of getting old. Okay. Which of the following statements about the series is true? The series diverges by the nth term test. So by the nth term test, the limit as n approaches infinity of 1 over 2n minus n, that's going to be equal to 0. That does not prove convergence or divergence. So we can knock both of those out right there. It cannot prove. If the result is 0 of the limit of the nth term test, it can't prove either convergence or divergence. It can still diverge or converge. It's just that we can't prove it using that. The series diverges by the limit comparison test. Um, hmm. Let's see. So this series diverges, right? This diverges. Okay, so let's run the limit comparison test. So the limit as n approaches infinity of 1 over 2n minus n times by n over 1. Through L'Hopital's rule, because this would be infinity over infinity, so through L'Hopital's rule, if we take the derivative of the top, that's going to be 1. If we take the derivative of the bottom, the derivative of 2 to the n is the natural log of 2 times by 2 to the n. And then we'd have minus 1, right? Yeah. Well, that's going to be equal to 0, which does not equal a constant. So limit comparison tests didn't show us anything then. So it's going to have to be D, but let's just go ahead and make sure. This converges. This is a geometric series. And the ratio is 1/2. So let's use the limit comparison test. So the limit as n approaches infinity of 1 over 2n minus n times by 2 to the n. Well, I mean, similar. You use L'Hopital's rule. Honestly, if you just want to look at it, also you can just kind of see the leading terms. 2 to the n over 2 to the n, that's going to be equal to 1. But following L'Hopital's rule, the derivative of the top is natural log of 2 times by 2 to the n over natural log of 2 times by 2 to the n minus 1. If you take the derivative again by L'Hopital's rule, this is going to be, well, this is a constant, right? So the derivative of this is the natural log of 2 times by 2 to the n. So you just get natural log of 2 times by the natural log of 2 times by 2 to the n. You'd get the same thing here. This would become 0. Well, then it's just going to become a ratio of 1 to 1. So this is just going to be equal to 1. There you go. So we showed here we get a constant that's going to be, so 1 is less than infinity, it's greater than 0. Therefore, this series converges if this series converges, or diverges if this one diverges. So in this case, it converges. There you go. The power series given here, so a sub n, which we don't know, but yeah, converges at x equals 5. Which of the following must be true? So this converges at x equals 5. The center is at 3. So if I set it up kind of like this right here, the thing is, what I don't know is I don't know if this is an endpoint right here. I don't know if that's an endpoint. It could still, so I do know that it converges at x equals 5, but I mean what's hard is that it could extend further. I mean, it could extend to like something like 6. But with that being said, I at least know here that so if I think about it, if my center is at 3, right? So my center is 3. Let's say this right here. So the center is at 3. I know that it converges at 5. Which would, so that's a distance of 2, right? So if I follow that logic, the radius has to at least be that, correct? So then I could say to 1 it would also have to converge here. Um, well, actually, I don't know if it does converge at 1. But I could say that it could converge at 1. I do know that it converges at 5. 5 could be the endpoint, but that would mean that 1 could be the endpoint, but I don't know if it converges or diverges here either. So the series diverges at x equals 1. I don't know if we can say that for sure. The series converges at x equals 1. We're not sure. The series diverges at 0. So 0 goes beyond here. Again, we're not sure if these are endpoints, so it could extend further. So I don't know. But the series converges at 2. Well, 2 is within this interval, right? So 2 would be like right here. So yes, if it converges at 5, and we're not sure if it converges at 1, but we at least know the radius here is 2, then for sure 2 falls into that radius. So for sure we know that the series converges there. Okay, last couple questions. What is the radius of convergence here? Okay, so before you go and run the ratio test, which you definitely could do, I'm just going to turn... This is just a... It's just a geometric series. Put everything to the n power, right? So I can write this as x minus 4 squared over 3 raised to the n power. That n could go here, making it 2n, and it can go here, making it 3 to the n. So here's my ratio. So x minus 4 squared over 3, all that has to be less than 1, right? Multiplied by 3. So x minus 4, I'll say squared, has to be less than 3. I can take the square root. I'll get x minus 4 has to be less than the square root of 3. There you go. I think we have our answer. The square root of 3 is our radius. When you have x minus c is less than r, this is the radius, so r is equal to the square root of 3. Show if the following series converges or diverges by using the integral test. Okay. So, the limit as n approaches infinity of the integral from 3 to n of 1 over n squared plus 9. That should be x. X squared plus 9dx. Ooh, you guys are not going to like this one. Oof. Yeah, you guys aren't going to like this one. Let me go way back and remind you guys. The derivative tangent inverse of x is equal to 1 over x squared plus 1. So my aim is to show that this fits this right here, and I can use the antiderivative to get tangent inverse, or arctangent. So how am I going to do that? I'm going to factor out a 9 from both of these terms. So from the denominator, so I'm going to make it 1/9 out here. The limit as n approaches, I'm telling you guys, the hardest part about calculus, I've said it before, the hardest part about calculus is the algebra. So this would become 1. If I factor out a 9th from that, this becomes x over 3 squared plus 1. So let me just follow some algebra logic here. This right here is x squared over 9 plus 1, right? but I factored out the 9, so if I redistribute, that becomes x squared plus 9. So just kind of showing the backwards work of that right there and how I get that. Okay? So the reason why I write it like that, though, is because this has a coefficient of 1/3, which means that's going to be my chain rule. My chain rule is 1/3. Okay? So I get 1/9. I get the limit as n approaches infinity. The antiderivative of this is going to be tangent inverse of x over 3. But I also have to divide by 1/3, which is the same thing as multiplying by 3, because that's the chain rule here. So again, if I take the derivative of this, what's the derivative of tangent inverse? It's 1 over x squared plus 1. Well, my x is actually x over 3. I would also have to multiply by 3, right? So yeah, I'd have to multiply by 3 because of the chain rule. Yeah, I think that makes sense. Checks out. So I have to multiply by 3. So let me just do the backwards work right here to kind of show you. So the derivative would be 1 over x over 3 squared. So this is 3 on the top because of this right here. Plus 1 times by 1/3, which is the derivative of that inside right there. That would cancel, giving me what I have right there. Okay. Told you guys wouldn't like it. Alright, so I'm also going to bring that 3 out there. That's going to make it 1/3. So it's going to be 1/3 limit as n approaches infinity of tangent inverse of x over 3. This is going to be evaluated from 3 to n. So let's plug in. So I have 1/3 limit as n approaches infinity. If I plug in n, that's going to be tangent inverse of n over 3 minus tangent inverse of 1. Okay. Now again, you guys are still not going to like this right here. Tangent inverse. Tangent, if you think about all those tangent lines, goes from negative pi halves to pi halves. Tangent inverse, then, the range goes from pi halves to negative pi halves. I'm pretty sure we had a question like this on like the very first test, not going to lie. Again, so I wouldn't expect you guys to remember this, but we have covered this before. But as n approaches infinity of this expression, it's going to be equal to pi halves. So that's how I can do that algebraically. So that's going to be pi halves. This one I can think about trigonometry. What's this going to be equal? What is tangent inverse of 1? Well, if I think about that using trig, if tangent inverse of 1, this right here is going to be equal to some angle theta, then tangent of theta is equal to 1 over 1. Tangent is opposite over adjacent, so which means the triangle I'm using is a pi-4th triangle, 1 to 1. This is pi over 4. Therefore, that angle right there is pi-4ths. Okay. This is a rough one. Sorry, guys. But it's a good one, too, to remind you guys of all this. 2 pi over 4 minus pi over 4. That's going to be equal to 1/3 times by pi over 4. That's going to be equal to pi 12ths. So, show if the following series converges or diverges using the integral test. State the conditions of the test. Ooh, haven't done the conditions. So, conditions. Positive. Continuous. Decreasing. For f of x. I don't have a lot of room. Sorry, I'm just going to say it. Fine, I'll write it. The integral converges. So the series converges. I promise you're going to want to be more specific on the AP exam. Okay? But there you go. There you go. 27. Use the ratio test to determine whether the given series converges absolutely, converges conditionally, or if it diverges. Okay. So, absolute convergence means that the absolute value of this, if it converges, then it converges absolutely. Now, this series being an alternating series could converge, but the absolute value of this, which would be this series right here, could still diverge. And if that's the case, then it only converges conditionally. Yeah. But if they both diverge, then the series just diverges. So let's use the ratio test. So we're going to run the limit as n approaches infinity. The absolute value, I'll be explicit about this rather than implicit. N squared, absolute value, so the series n equals 1, infinity, the absolute value, negative 1 to the n times by n squared plus 9 over e to the n is equal to n equals 1 of n squared plus 9 over e to the n. Okay, so I'm being explicit about that. Now let's run the ratio test. So the limit as n approaches infinity of n plus 1 squared plus 9 over e to the n plus 1 times by e to the n over n squared plus 9. So this right here is going to be equal to 1 over e. I'm actually going to bring that out as a constant. So 1 over e. Then I'm going to have n plus 1 squared plus 9 divided by n squared plus 9. Both of the numerator and denominator are polynomials of degree 2, which means that the ratio of them is going to be equal to 1. So this will just be equal to 1 over e. And this right here is less than 1, so therefore the series converges. And it converges absolutely. Because we tested the absolute value of this series right here. This series right here, the absolute value of my series, converges. Therefore, this series has to converge absolutely. If this ended up being divergent, but if I could still show that this one converges right here by using like the alternating series test, then it would converge conditionally. Okay? Okay, we are done, guys. I hope this helps. Let me know if you have any questions.